Mr. Chairman, for the introduction. Good afternoon to everyone. Also, first, I would like to thank the organizers for giving us the opportunity to present our results. So, as you can see, as a graphical abstract of my today's talk, I choose this word nano. So I wrote it by atomic force microscopy-based scratching lithography in a single. Sorry, I have to change. In a single layer of graphene. And this is just an example that atomic force microscopy is a very nice technique for mechanical manipulation of two-dimensional materials. And in this presentation, I will try to show you our results, how to use atomic force microscopy in order to study wear and fracture of graphene and wear protection by graphene. Okay. So this is the outline of my talk. So in the first part, I will briefly introduce you with graphene and atomic force microscopy. And then I will consider three different cases. So wear of homogeneous graphene, wear started and initiated along graphene edges, and wear in chemical vapor deposition graphene and influence on wrinkles on the resulting wear. Okay. So the first question is, why did we study graphene at all? So graphene is a single layer of carbon atoms arranged in a honeycomb lattice. It is atomically thin material, so 0.3 nanometer is the thickness of the graphene. And the first important thing, graphene has excellent mechanical properties, so measured by AFM nano indentation on free standing graphene, so elasticity of the graphene is around 1 terapascal. Then graphene is a part or single layer of graphite, which is well-known solid lubricant used for friction reduction. And also important thing is that graphene is impermeable to small gas molecules, so we can cover our metal with graphene in order to protect it from oxidation and from corrosion. So all these features make graphene very popular for making various protective coatings at the nanoscale. Okay. So here we'll consider two types of graphene. First one is produced by the mechanical exfoliation. This is very simple, very easy method where graphene is just peeled off from thick graphite and then exfoliated onto, let's say, silicon dioxide substrate. This is very easy method. It provides us with It provides us with good quality of samples, but the problem is that the lateral size of this flake is very small, at least around tenths of microns. So next method, you can go now down. The next method is chemical vapor deposition. This is simple, a robust method for the production of large area graphene. In this method, graphene is grown first of metallic, for example, nickel or copper foils, and then transferred on desired substrate. But first problem is that CVD graphene is polycrystalline material, so it consists of this, you see here, network of monocrystalline grains which are separated by these grain boundaries, which are defects in the graphene. And okay, let's go next. Here we are interested in the second type of defects in graphene. These are so-called wrinkles. They appear during fabrication, after the high temperature growth, during the cooling down, because copper and graphene have different thermal expansion coefficients. Copper shrinks more, leaving this network of out-of-plane graphene deformation. Okay, and as I said, since we want to study efficiency of graphene as a protective coating at the nanoscale, we need appropriate tool, and for this purpose we use atomic force microscopy. This is a basic setup, so we have piezo scanner which holds sample holder and sample. Then as a probe we have cantilever with this sharp AFM tip. And for the feedback loop, we have a laser which is focused on the top of the cantilever. Reflected light is collected by this 4-segment photodiode. And then we have system for automatic control where we can set desired set point, that is normal force between the tip and the sample. Okay. And the basic imaging mode is imaging in so-called contact mode. Here the tip is really in the contact with the sample, and this normal force is kept contact during the scanning. And in order to keep this force constant during the imaging, this scanner with the sample is moving continuously up and down in Z direction, and practically this movement of the scanner in Z direction is proportional to sample topography. Okay, and in addition, during the imaging, obviously there is a friction force between FM tip and the sample, and this friction leads to the lateral torsion of whole cantilever. So this we can measure this torsion, and this torsion is proportional to the lateral or friction force in our system. Okay, and if we further increase normal load, we will not image our sample, but we can make such, for example, like this straight trench in the surface. So this technique is very useful in order to study wear at the nanoscale. Okay. So first topic is wear of homogeneous mechanically exfoliated graphene. Okay, let's go next. Okay, so these are our results measured after the scratching. So this is graphene, and this is and this is neighboring silicon dioxide, which acts as a substrate. So we scratched these 6 square domains. Okay, next please. And okay, this figure shows height of these domains along these dashed lines, and here you can see domain depth as a function of trench number and normal force during the scratching. And practically we see two possible scenarios. For domains 1, 2, 3, 4, and 5, you see that the topography is rather flat, smooth, without any bumps. So here, practically, as shown here, graphene is just plastically deformed, as well as the silicon dioxide substrate beneath the graphene. But for the domain 6, as normal force is above around 10 micronewtons, you see graphene was torn, cut somewhere here, and then peeled off from the substrate. So this is the case of graphene wear. Okay, and next we wanted to try to explore efficiency of graphene for possible wear protection of underlying substrate. Okay, so we started with thin graphene with thickness of around 1 nanometer. This corresponds to single or maybe bilayer graphene. And as a method, we use nano indentation. So practically here, AFM tip is just moving in normal direction. We increase normal load in order to induce some deformation. And okay, next. These are our results. So by nano indentation, we made these 2 5x5 matrices. In this left part is graphene covered silicon dioxide, and here is bare silicon dioxide. And this figure shows height profile along this line. So what you can see is that the wear depth of this point-like trenches on graphene-covered surface is lower than on bare silicon dioxide. So, okay, thin graphene cannot be used for wear protection, but at least at some point can enhance mechanical load capacity of the underlying substrate. Okay, and then next try was with a little bit thicker graphene, so 4 to 5 nanometer. So these images are taken after the scratching. So in both images we have graphene covered surface and bare silicon dioxide. So graphene covered surface and bare silicon dioxide. And as you can see, we scratch these square domains with they are deep around several nanometers, but if you take a look in the graphene surface, which were also scratched for the same normal forces, practically graphene surface stayed intact. So practically we have at some point perfect protection by graphene. Okay, and this graph shows a summary of all of our results. So on y-axis is shown normalized wear depth, and on x-axis is shown normalized force. And these red dots are wear depth for bare silicon dioxide. If we cover the surface with thin graphene, we can decrease the wear, but only with thick graphene we can obtain practically perfect wear protection, because practically we had zero wear depth. Okay, this holds up to some normal, maximal normal force, after which we observed also wear of thick graphene. Okay, and just illustration of these processes. So for when you have thin graphene, we just decrease wear depth, but okay, next one, in order to have perfect protection, we need multi-layer graphene. Why? Because multi-layer graphene is described with these repulsive van der Waals forces, and practically we can describe these forces. They behave like airbags, so they prevent transfer of the deformation from the top to the underlying underlying sample. Yeah. Okay. So now next I will consider wear of graphene initiated from graphene edge. Okay, next. And the procedure is following. So I scratch the surface starting from bare graphene across the graphene edge onto graphene. Okay. And this is result for the normal force of around 100 nanonewtons. So this is topography during scratching, lateral force during scratching, and topography measured after the manipulation. And you see both in topography and also in the lateral force, there are sudden, let's say, cuts, discontinuities, and after that, AFM tip continuously pushes this graphene edge. This process is described by increased lateral force. You see this dark contrast, and after that, when we measure the topography, you see this bright line, which correspond to graphene wrinkle, which is graphene plastic deformation. Okay, next. And if we further increase the normal force to around 120 nanonewtons, we practically observe complete wear of graphene. So this is topography during scratching, this is lateral force, and this is zoom out image made after manipulation. So we scratch the surface in this square domain. Practically graphene was torn somewhere here, and then AFM tip just pushes, pulls and left this graphene somewhere here, this bright domain. Okay. And during these manipulations, we measure lateral force. So as I said, this lateral force corresponds to the lateral torsion of the cantilever, and is proportional to the friction in the system. And every of these steps, okay, I didn't have time to consider the first two, but all of these manipulation steps were characterized with strong increase of the lateral force during the manipulation. And okay, this is summary for all of our experiments. So this increase of the lateral force as a function of distance, and practically we can distinguish between four processes. In the first two, graphene edge is in the elastic regime. After that, we have plastic deformation and wrinkle formation. And when we reach this lateral force of around 50 nanonewtons, which is practically, I forgot the word. Sorry. We have complete fracture and peeling of. Yeah, this is practically tensile strength. Yeah. After the tensile strength is reached, we have fracture and complete peeling of graphene. Okay. And for the final segment, we have wear of CVD graphene. Okay, let's go next. So, as I said, chemical vapor deposition is a very nice method for the production of large area graphene, but it is characterized with these out-of-plane deformations, which are called graphene wrinkles, and you can see them as these bright lines both in topography and phase image. And in order to study their influence on wrinkle, we applied the following procedure. Let's go next. So this is zoom-in image with. So this is wrinkle, this is wrinkle, this is wrinkle, okay? And this is our procedure. So we start with some initial normal force, and every next domain we increase normal force in order to initiate wear of graphene. And these are results measured after the scratching. So this is phase this is phase image, this is current image, and as you can see, there are two domains, 1 and 2 here and here, which have completely different contrast than the rest of the graphene. And this inset show the topography for this part, and you see these two dark triangles. Their topography, their thickness is around 0.5 nanometers less than the surrounding area, so graphene is peeled off from this part. So this means that this phase contrast corresponds to underlying silicon dioxide, and this is the reason why we measured zero current, because silicon dioxide is obviously insulating material. But for us, the most important thing is that you see where was initiated here, and here, and these are exactly position of the wrinkles. So wrinkles are weak points for the wear resistivity of graphene. Yeah, that's the problem. Okay. And just a short explanation. So wrinkles are autoplane and plastic deformations, and they are described with various types of defects or even change of hybridization in graphene. And these defects degrade mechanical properties, leading to decreased wear resistivity. Okay. And as a conclusion, we believe that graphene could be used as efficient protective coating at nanoscale. We observed that we measured that the normal force which initiated wear for homogeneous graphene was around 10 micronewtons, but the problem arises if you have some defects such as graphene wrinkles or exposed graphene edges, then this normal force decreases by at least 1 or even 2 orders of magnitude. So this is a problem which should be solved. Okay, I just want at the end to acknowledge people involved with the work and this project, and sorry for this problem with the presentation. Thank you for your attention.
Can you stay here during the discussion and open So thank you very much. We start now the discussion of the presentations, and we will start with the current presentation. Are there any questions? Yeah?
I was just
okay. Yeah.
Yeah, thanks. It was surprising for me that you don't found the people.
For me. This is a question for me.
Yeah, for the first, yes? For the first division modeling.
No, I'm not.
For the first of
No, we start with the current.
The last.
Last. Already open. We come immediately to thank you for the Can you stay here, Mr. Vagic?
Sorry.
We have now the discussion of your paper.
Okay.
Yeah? Is there a question to the current paper? I would have a question. You didn't speak about the thickness of the graphene layers.
Yes. It's about
how can you control it when you produce it by just pressing graphite on a silicon surface?
Sorry, your question is how can we control the thickness of the graphene?
Thickness and what is the thickness?
Okay, the basic method is this micromechanical exfoliation from graphite when you peel it off from graphite. But you can make it thinner and thinner if you repeat this procedure until you make it single layer. I mean, this is the procedure which applied Nanoscale and Gaim and who then awarded with Nobel Prize. So very easy. They call it Scotch tape method. It's very easy. Okay, as I said, it is not for realistic applications, but for research, for labs, it works.
But you have now different experimental results on the wear resistance and so, but doesn't that depend on the thickness of the graphene?
Thickness is theoretically 3.4 angstrom, so 0.3.
If you have only a single layer?
Yes, single.
Yeah, and you did have only a single layer?
Yeah, here I consider on single and bilayer, and when I consider thicker graphene, it is 4 to 5 nanometers, let's say around 10 layers.
Okay. Any other question? Yeah.
I have the question about the multi-layer graphene, because you showed some image with these van der Waals forces, and you said that these are negative, right? These are negative.
I said they are repulsive.
Repulsive. So
yes.
They are really repulsive.
Yes. I mean, when two neighboring graphene layers tend to approach each other, then these van der Waals forces become repulsive. Yes.
Okay, thanks.
Okay, any other question?
On about your graphene made by CVD, I'd like to know the effect due to the source gas. So maybe you use a hydrocarbon gas to make CVD. Sorry, to use CVD.
Sorry, we are not making a CVD graphene. We got it from Spain. So
Oh, yes.
I'm not experienced with chemical vapor deposition, sorry.
Okay, thank you very much.
Okay. Any other question? Okay, so it's not so okay. Shall we then move to okay.
One more question,
Sorry.
please.
Yeah.
Thank you. I would like to ask, is this possible to use this method for examination of resistance to wear of some other materials, for example, organic coatings of thickness maybe of several microns, like paints?
Yes.
Okay, thank you. Thank you.